So here's y squared plus 2y plus k equals 0. Of course, for GeoGebra, I need an x instead of the k, and it gives me this thing, right? And there's my bifurcation diagram that we drew by hand. We can put in, I'm not going to tidy everything up, but we can put in some vectors to indicate which way things were going. And we knew when k equals 0, this was up, that was down, and this was up. And that's enough to define both sides of the whole thing, right? So my arrows are up out here, arrows are up down there, and arrows are down inside there. And we have a node, my point. There's my point. We had a node right there, right? And so everything outside here is up, everything inside the parabola is down. That means that this curve along the top is a source, this curve along the bottom is a sink. So that's that picture. And then here's the picture from the third one. We had these two curves. We know that we had two nodes, points. We had a node here at -2, -1, and a node here at -2, -1. And then we can also say, let's go back to the algebra and say, well, let's graph y squared minus xy plus 1 equals 1. And this will give us the place where dy dt is positive. And that's everything in this region. So what that tells us then is that the blue curves are in the region where dy dt is positive. So if we're going to put in some vectors here for our phase lines, it would be pointing up in here. Right, so those are all pointing up. And then in here, because we know that it's 0 on the green line, it's positive in the regions where there are blue lines, so it's going to be negative over here. It'll be negative like that. And there's our phase line. So there's our bifurcation diagram. Oh, and to get away from this, so there's a bifurcation diagram. We want to hide one of these things. Vectors, there it is. So there's a bifurcation diagram. So they're pretty easy to build with GeoGebra. I don't know how to get, say, what I'd like to be able to do is say this top half would be red because that's a source, and this bottom one to be green because it's a sink. I don't know how to quite do that in GeoGebra. So I'm not going to do that. So let me pause for a minute. So this is another example which is on the sheet, and we'll come back to this, but dy dt equals y minus 1 cubed plus ky squared, right? And we set the k equal to an x to be able to graph it. And here's the graph that you get. And this is one that's not an easy one to do by hand. So here is our graph. We took dy dt, set the right-hand side equal to 0, had GeoGebra graph it. Which way are the arrows going? Well, we take our dy dt, which is y minus 1 cubed plus xy squared, and we say, well, we'll set that to be a positive number, say 1, and we get some curves. And the blue curves are where it's positive. So we know up in this region to the upper right, dy dt is positive, so our arrows are going up. In this curve down to the lower right, dy dt is positive, so our arrows are going up. And in this whole big space out to the left, dy dt is negative, so we're going down. So what do my arrows look like? If I put in some arrows, some vectors, right? We're up here, and we're down out here. So what does that tell me now if I'm trying to understand what's going on with this system? Well, this curve, the one that's sort of labeled equation 1, that's always going to be a source because it's always away that way and always away that way. This curve here comes into existence somewhere over there, right? So we'll put in a point right about there. And that's a node because if we draw in the vertical line through there, it's going down here and then down again there. And so to the right here from G up to the right, this is down above and up below. So this is all a sink. And then down here, you're going up away from it and down away from it. So this is a source. So we always have this source, and I get to about, I don't know, 6.7, and then a node just pops into existence and immediately splits into a source and a sink going to the right. One thing that we have, I do want to point out here is that suppose we take dy dt to be arctangent of y minus x, and we set that equal to 0. We get that curve, and that's actually a really, really common curve. It's one of the branches of tangent of x, right? So if our dy dt is arctangent of y minus k, when we set k equal to 0, we get the tangent curve. And we can, of course, ask ourselves, where is it positive, where is it negative? Arctangent of y minus x equals 1. That's that red curve. So we're positive here on the right. Vectors. Positive here and negative here. So let's see. I suppose I'm going to just delete all those, and that gives me my just arrows. So this green curve here is all just sinks, and we know that because if this is a tangent curve, there's going to be a vertical asymptote at pi over 2. To the left of that, there's no sources or sinks at all. To the right of it, there's no sources or sinks at all. So what we have then, if dy dt equals arctangent minus k, is you get a no equilibrium at all. Actually, we're starting from the left, no equilibrium at all until you get to minus pi over 2. And then way down at minus infinity, sort of, our source pops into existence and it climbs up. And when you get to pi over 2, it just zips off to infinity and disappears. And as k is bigger than pi over 2, you just have everything going down. So going back to our diagram here, right? So we found this by using GeoGebra, and we did this. And why is this the inverse function of arctangent? So this is one of these interesting things about these cases where you have a function minus k but that becomes arctangent of y equals k. And if you take the tangent of both sides, you get y equals tangent of k. So this equation is the inverse of that equation, right? So our bifurcation diagram is this. That's because k equals arctangent of y is that. And so the reflections of each other along the line y equals x. And so we actually saw that happening here, right? This curve here was y squared plus 2y. When we got the bifurcation diagram, it's y squared plus 2y just flipped over the graph y equals x. So this curve and this curve are related to each other because they're inverse relations of each other. And that's what plus or minusing by k does if you just have that particular type of bifurcation diagram. So in general, if you dy dt equals f of y minus k, that's the graph of the inverse relation to f of y, because if you solve f of y minus k, f of y equals k, which is solving this when dy dt equals 0, then y equals f inverse of k. If you have a function, that's fine. Sometimes you don't have a function. That's why we sort of technically call it an inverse relation. Quadratics don't have inverse functions, but you can take a graph of a function and flip it over the line y equals x, and that gives you the inverse relation. So that is some stuff about bifurcation diagrams.